Is it okay? Yeah. So first of all, welcome everybody. I apologize for the early hour. It's the organizer's fault. So. Also, you know, Arshak Petrosyan apologizes. You know that he couldn't come. I mean, he tried making it, but he couldn't. So he asked me to apologize on his behalf for not being here. Anyhow, I will, in this last of the 4 lectures of Arshak, I will talk a little bit about the lower dimensional obstacle problem. And since both Eugen and Henrik have already talked a lot about, you know, the type of ideas that are involved, I will try to give you an overview of what's known about this problem. This is also usually known as the Signorini problem. And if time allows, which I doubt very much, especially given the fact, so I have 50 minutes now?
Yeah, 52.
Okay, so if time allows, but I don't think I will be able to. I wanted to talk a little bit also about some recent work on the parabolic Signorini problem. So the study of the classical obstacle problem started in the 60s with pioneering works of Stampacchia, Hans Levy, Jacques-Louis Lyons, and you know, it has led over a period of 3 decades to beautiful and deep developments in calculus of variation and geometric PDEs. The crowning achievement has been the development back in the mid-70s due to Luis Caffarelli of the theory of free boundaries. And in this theory, the obstacle problem occupies a kind of primary position. So you have seen already in the lectures of Henrik, you know, quite a bit of development on that subject. So over the past few years, there has been some interesting progress in the lower dimensional obstacle problem, and I will illustrate this problem soon after. This is also known as the Signorini problem. It was proposed by Antonio Signorini in the 50s, and I will tell you a little bit about the story of Signorini later on. So, well, I've already said this. So the part of my discussion which has to do with, you know, there will be an overview, as I said. So, and I will also talk about the analysis of singular free boundary problems in the Signorini problem, and that is joint work with Arshak. And there is also some recent work that you can find in archive with Donatella, Arshak, and Tung To on the parabolic Signorini problem. Okay, so this paper is available. You can grab it from archive. So let me introduce the lower dimensional obstacle problem. So I will let me keep the beautiful picture of Juan Luis. So you know, just think of a situation like this. You have a domain in Rn. Let's think of it as a ball, for instance. So this is our ground domain, and this domain is separated by a codimension 1 smooth manifold M. And on this manifold, we have 2 functions, okay? So think of a function phi, which is defined on the manifold, and that will be our obstacle. So the obstacle lives on a lower dimensional manifold. Usually when I give this talk, somebody in the audience always asks me, why codimension 1? Because if you take higher codimension, the problem becomes trivial because of removability of singularities of harmonic functions. So codimension 1 is the only interesting case. It's as low as you can go. If you have higher codimension, then the problem becomes trivial. So here you are trying to minimize over a class, so we are minimizing the energy integral here over the closed convex set given by all W12 functions, which are equal to G on the boundary of omega. So G is the boundary value, and U is bigger than or equal than phi on M intersected with omega. So the picture looks like this. So this is a picture that you have already seen several times in this workshop, so I will not dwell too much on it. The main difference from what you have seen yesterday with Henrik's lectures and this lecture is that the obstacle is defined on a lower dimensional manifold. Okay, so you don't have an obstacle which is defined on the whole domain. So this is known as the lower dimensional, the thin obstacle problem. The thin obstacle is the function phi, and the picture is like this. So this picture is taken from the book by Arshak, Henrik, and Nina Uraltseva. And so that's the picture. And of course, you know, when U is constrained to say above an obstacle which is assigned on the whole domain, then you have the classical obstacle problem. This problem, the classical obstacle problem, is to a large extent quite understood. There are still some fundamental questions which are open and interesting. But the thin obstacle problem, on the other hand, has been studied only very recently because there are several challenges, new challenges that arise in the analysis of this problem. So this is a picture that gives you an idea of possible solutions of the thin obstacle problem. So here, in both these pictures, the obstacle is the zero function. Okay? So, and you see that the lower dimensional manifold, which is this purple shaped object here, is a flat manifold, which is a case to which I will go back quite often in this lecture. And so you get these two special solutions of the obstacle, of the thin obstacle problem. Okay. So there is a variety of situations from the applied sciences in which this problem arises. In elasticity, when an elastic body is at rest, partially laying on a surface M, so like in that picture over there, then there are some very interesting problems in financial math where this situation arises. And there are also, you know, problems in fluidodynamics. If you look at the book by Duo, the classical book by Duo and Lyons, you'll find several interesting physical models which go back into this framework. Okay. Actually, this one, the last model here, is particularly relevant when you study the parabolic Signorini problem. Okay, so back in 1979, Luis Caffarelli had already proved this fundamental result. So if the manifold and the obstacle are smooth, then Caffarelli showed that the unique minimizer in the thin obstacle problem is of class C1 alpha. So this is omega plus, this is omega minus, this is your manifold M on which everything takes place more or less. And so what happens with the solution is that the solution is C1 alpha up to the thin manifold. Don't think that the solution is C1 alpha across the manifold. So the gradient has a discontinuity across the manifold, but if you go from this side or this side, then the gradient is continuous up to this codimension 1 manifold. So since one can make free perturbations away from M, it's very easy to see that here the minimizer is a solution, is a harmonic function. Okay. Of course, you know, the minimizer is not harmonic in the whole domain. But it will be harmonic in the whole domain if you take a higher codimension manifold because of removability of singularities. That's why we don't study the obstacle problem when the manifold has higher codimension. So what you can show, and I will make this clear in a moment, is that the Laplacian of U is in the distributional sense less than or equal than 0 in the whole manifold. So the minimizer is a superharmonic function in the weak sense. Okay, so here are the so-called complementary or Signorini conditions. So U minus phi is bigger than or equal than 0 inside of omega. Then there is this condition on the normal derivatives. So when I write nu plus and nu minus, I will intend the outer normal derivative. So this will be nu plus, and this will be nu minus. So they are respectively the outer normal derivatives, unit normals to omega plus and omega minus. And then there is this other very important condition that says that U minus phi times d nu plus d nu minus is 0. Okay, so of course, you know, one of the main objects here of interest is the so-called coincidence set, which is the set in M where U coincides with the obstacle. So that would be in this picture, this would be the coincidence set, which I've denoted with lambda. And then there is the boundary in the relative topology of M, which is the free boundary. And this is a priori unknown. So when the lower dimensional obstacle is identically 0, so the constructions and the proof are more transparent. The situation becomes quite more complicated in the case of non-zero obstacle. And this is what makes the first big, huge difference with the classical obstacle problem. In the classical obstacle problem, as Henrik has indicated in his lectures, it is quite customary, by now quite standard, to normalize the problem. So you subtract off the obstacle, you assume that the obstacle has enough regularity, you subtract off the obstacle, and then you reduce the problem to 0 obstacle. Okay? Here, when you do this, the situation becomes complicated, quite more complicated, for reasons which I hope I will be able to illustrate later on. So I will mostly stick with the case in which the obstacle is 0 and the manifold is flat. Okay? So I will also assume from the start that M is a flat portion of the boundary of the relevant domain. So think of the initial domain as just of this part here. Forget about omega minus for the moment. And so in this case, the obstacle problem is known as the Signorini problem. So Antonio Signorini, who was an engineer and also a mathematician, so he posed this problem during a course which he taught at the Istituto Nazionale d'Alta Matematica in 1959. And he called the problem with ambiguous boundary conditions, since, as I showed you before, there is a set of boundary conditions which the solution must satisfy. And so Fichera at the time was a student in the course, and he was thinking about this problem when Signorini became quite seriously ill. And so the story goes that Signorini wished to know the answer to his question before his death. And in January 1963, Fichera was able to give a complete proof of existence of uniqueness of the solution to the Signorini problem. And he presented his note to Signorini just 1 week before his death. So Signorini told his family doctor, "My student Fichera gave me a great joy." And the doctor said, "But professor, you had so many joys in your life." And Signorini is known to have said, "But this is the greatest of all." And apparently these were his last words. So there is quite, you know, an intense story behind this problem. So let me go then to the normalization. So I will think of situation of zero obstacle. Okay, so from now on, my domain omega, is it okay if I erase your beautiful picture? I knew you were going to retaliate. So from now on, let's just think, since, I mean, I will discuss, at the beginning I will discuss, this is, everything I talk about is a local question. So I will think of omega being just a unit ball in Rn. So this will be B1 plus, B1 minus, and this is xn equal to 0, and this is going to be my manifold. So I'll take a flat manifold M, which will just be the hyperplane xn equal to 0. And I will denote by, so this is B1 prime, will be the thin manifold. Okay, so it's the intersection of the unit ball with xn equal to 0. So as I've said already, Caffarelli had proved the C1 alpha regularity up to the thin manifold of the solution. Okay, so it's the solution to the Signorini problem satisfies the Laplacian equation in B1 plus. U is bigger than or equal to 0 on the thin manifold, and the normal derivative is less than or equal to 0, and u times du dxn is 0 on the thin manifold. So I will assume that 0 is a point of the free boundary. Okay. And I will denote by this script C here the class of solutions to this so-called normalized Signorini problem.
Let me ask this question. You do not care about what happens downstairs?
No, as you will see in a moment, I can, because of the conditions, I can reflect by, I can make an even reflection in Xn, and then the solution becomes a solution to an interior Signorini problem. So, you know, as I just said, you can reflect by even symmetry in Xn, and then the resulting function will satisfy this condition, Laplacian u less than or equal than 0 in B1. Laplacian of u is 0 in B1 minus the coincident set, and u times Laplacian u is 0 in B1. So it is also useful, this relation is very important. This is just integration by parts, and but it's very important because in the theorems which I will state in later on, this equation here plays a very important role. So notice that because of this equation here, since we know that du dxn is less than or equal to 0 on the flat manifold, then in particular we know that Laplacian of u is less than or equal than 0 in d prime. Okay, so that's where this comes from. You first prove this thing here, and then you use the Signorini condition to infer this fact here. So u is a superharmonic function in B1. So the first breakthrough into this problem came in 2004 with a beautiful paper by Athanasopoulos and Caffarelli, in which they proved that the solution to the Signorini problem is C1 1/2. So the gradient is Elder continuous with exponent 1/2. Now this result is sharp, is the optimal regularity because, oh, by the way, I should say that David Richardson had already proved this result in 1979 in his unpublished PhD thesis. His thesis is available online. If you Google David Richardson, you'll find his thesis at the University of British Columbia, 1979. Okay, it's a beautiful little piece of work, but he never published it. So, but it's confined to n equal to 2. He was using complex variables to establish his result. So, as Richardson had already proved this result here in 1979 in two-dimensional case, but going from 2 dimension to higher dimension was a big challenge, and the breakthrough came in 2004 with this work of Atanassopoulos and Caffarelli. So as I said, the regularity is best possible because if you look at this guy here, which is one of the two solutions which I've already showed you before, then you see that this function here, which is a solution of Signorini problem with zero obstacle on the flat manifold xn equal to 0. Okay? So this function here has precisely this type of regularity here. So you can't get better than that. So a different perspective on the Signorini problem came in 2007 with another very important work by Atanassopoulos, Caffarelli, and Salsa, in which for the first time they made the connection from, between the Signorini problem and a fundamental formula that was proved by Almgren in 1979 in his study of minimal surfaces, which is the so-called Almgren's frequency formula. So Almgren introduced this quantity here. Let's say that U is a harmonic function. If I want to use more blackboards, well, I will erase this piece here and just.
One thing you can, no. You cannot do it if you combine the blackboard and the.
Huh? Okay. All right. Well, I'll erase this because by now everybody has looked at this picture. So Almgren noted this remarkable fact that if you take a harmonic function, say in B1, then that quantity over there, which he called the frequency, is monotone increasing. And the proof of Almgren's result is very simple. I'll just give you a quick illustration. If you look at the logarithmic derivative of n, which is this thing here, then you see that if we call d the Dirichlet integral of the function, and the h the height of the function, then the logarithmic derivative of d is just this one. Notice that there is this factor of r there, and that factor is important because it makes that quantity scale invariant. Okay? So if you rescale your function u, then the frequency does not change. So then if you do a little bit of computations, you can show that this is n minus 2 over r times the integral over br of normal derivative of u squared divided by d. Then you have plus 1 over r. There is this, and then there is h prime, and when you differentiate this function, you see you get n minus 1 over r, which comes from differentiating surface measure, and then you get minus, maybe there are numbers here, so, and then you get here the integral. So when I differentiate this guy, I get u nu divided by h. Okay, so this is the derivative of the logarithmic derivative of the frequency. And now you see that there is a little miracle happening here. Okay? And then the question is, so you want to show monotonicity of the frequency, so you would like to show that this is bigger than or equal than 0. So the question is, this is bigger than or equal than 0 if and only if this difference here is bigger than or equal than 0. Okay? But then you use the equation, remember u is harmonic, to recognize that the Dirichlet integral is given by this boundary integral here. I've used harmonicity. Okay? And therefore, non-negativity of this difference is, you see, this d here is the same guy that is up here. Okay? And then non-negativity of this quantity is equivalent to having u nu square, because this times this has to be less than or equal than this times h, which is u squared. And you recognize immediately that this is nothing but Cauchy-Schwarz inequality. So that shows that the frequency is a monotonic function of R on a harmonic function. What Atanassopoulos, Caffarelli, and Salza recognized is that if you have a solution to the thin obstacle problem, then with zero obstacle, then the frequency is still monotonic, like for a harmonic function. So in other words, the monotonicity of the frequency does not see the lower dimensional obstacle. And the reason for that is the Signorini complementary condition that I told you before. So you have to use them in your calculations. And you can show pretty much like I did on that blackboard over there that this quantity here is still monotone increasing on a solution of the thin obstacle problem with zero obstacle. So it is also quite immediate to know this. Remember, I showed you before, I observed that if u is harmonic, then the Dirichlet integral is also expressed by this boundary integral. So if you put this information in here, you see immediately that if u is a harmonic function which is homogeneous of degree kappa, then the frequency is identically equal to kappa. It's just this little observation over here. And you can reverse this information. If you know that the frequency is identically equal to kappa, then u has to be homogeneous of degree kappa. So the frequency is constantly equal to kappa if and only if you have homogeneity. Now this is a very important fact which is built into the Almgren's frequency function. Okay? So similarly to the classical obstacle problem, in the lower dimensional obstacle problem, the analysis of the free boundary revolves around the behavior of the so-called blow-ups, the rescalings that Eugen has discussed and Henrik has discussed at length. So the new thing that Atanassopoulos, Caffarelli, and Salza introduced in their 2007 paper is a new notion of rescalings. So up to that point, and in fact in the paper of Atanassopoulos or Caffarelli in 2004, the rescalings that had been used in the thin obstacle problem were the standard rescalings, the same one that worked for the obstacle problem, and Henrik has discussed this guy. Now, there was a new idea in the paper by Atanassopoulos, Caffarelli, and Salza. They said, well, instead of using this guy, let's use this as rescalings. Now, you see, this complicates the picture enormously because you're dividing by the L2 norm of the function at every scale, and you don't exactly know a priori how that behaves. Here you have just R squared, which is the the appropriate scaling when you work with the Laplacian. So, so they introduced these blow-ups, and of course the whole game then became getting a control of this rescaling function when you let R go to 0, when you zoom down. Oops, what did I do? Does anybody know how I get out of this trouble?
Window, view full screen.
Okay.
View.
Yeah. Okay. Full screen mode. Okay, thank you everybody. Thank you, Vincenzo. All right, so before I get to that, you should notice that these rescalings are tailor-made to have this condition here. So they are normalized so that if you take the L2 norm on the sphere of radius 1, that L2 norm is uniformly equal to 1 because I'm dividing exactly by this guy. So Generally, the blow-ups might be different over different subsequence, but you know, the following result provides a tool to controlling the rescaling, and that is the theorem that was observed by Athanasopoulos, Caffarelli, and Salsa, so that if you have a solution of the thin obstacle problem with zero obstacle, then Almgren's frequency is still monotone increasing. And it's constant equal to kappa if and only if U is homogeneous of degree kappa. Okay, so a key property of the frequency, which I told you before, is that it is invariant under these scalings. In other words, if I now take the rescalings UR, which were introduced by Athanasopoulos, Caffarelli, and Salsa, then you see that if you take n of UR at when R is equal to 1, this is the same as n of U at level R. Okay, so if we use this observation here, which is crucial in all this business, okay, one obtains the following. So let's take on a ball of radius 1 the energy of the rescaled functions. So this is equal to this, because remember now the rescaled function will have L2 height. Will have height equal to 1. So when it's here, I'm dividing by h of UR at level 1. So I have 1. So this is equal to this because of this, but by the monotonicity of the frequency, this is less than or equal to this. Oh, this tells us something very important, that the energies of the rescaled functions are equibounded. So you see, we have equiboundedness of the energies. All right, so using this fact and using compactness of the embedding of W12 in L2 of the boundary of the sphere, and using C1 alpha estimate proved by Caffarelli in 1979, one can show that there exists a function U0 which is not identically equal to 0. That's very important. And this function will be called a blow-up, which is you know, a limit of this sequence of rescaled. So we have convergence in W12, so we have strong convergence in W12. A priori from this thing you just get weak convergence, but then you know, you can work your way through and get strong convergence. We get convergence in L2 of the sphere, and we get convergence in C1 lock up to the thin manifold. Okay? So the monotonicity of the frequency also implies easily the following result, proposition. So if we have a normalized solution of the Signorini problem, denoted by U0 any blow-up of U as described above, then U0 is still a solution to the Signorini problem. It's a global solution in all of Rn, and it is a homogeneous. So that means that on xn equal to 0, it will satisfy the Signorini condition. And it is a homogeneous function of degree kappa, where kappa is the limit of the frequency of U at 0. So the following result, which is very important, as you will see, was proved by two groups of people. Part of it is in the PhD thesis of Luis Silvester, 2006, and part of it is in the paper of Athanasopoulos, Caffarelli, and Salsa in American Journal, 2007. So this is a lemma that tells you a gap condition. So when you look at a solution of the Signorini problem, then the frequency has to be always bigger than or equal than 3/2. The limit of the frequency is 0. Okay? Moreover, there is a gap. So if you have, if you look at this guy here, this number here, then it's either 3/2. I'm sorry for writing 3/2 in this funny way. You will see there is a reason for it. Okay? So it's either 3/2 or it has to be bigger than or equal than 2. So there are no frequencies between 3/2 and 2. Okay? So definition, given a solution to the Signorini problem for kappa bigger than or equal than 3/2, I told you then 3/2 is the lower threshold for the frequency. So I will denote by gamma kappa of U the collection of points of the free boundary at which the frequency takes the value kappa. Of course, here n at x0 is just a shifting of the frequency at 0. And I will always denote by this quantity here the limit. We know that this limit exists because the frequency is monotone increasing, okay? So the set gamma kappa of u may be empty for certain values of kappa. In fact, the gap lemma that I showed you before implies that gamma kappa of u is empty whenever kappa is between 3/2 and 2. There are no values, no possible values between 3/2 and 2. On the other hand, these functions here, if you look at the function real part of x1 plus I xn to the kappa, when kappa is either 2m minus 1/2 or kappa is equal to 2m, then these are solutions to the Signorini problem, okay? And 0 is a point of the free boundary which belongs to this set gamma kappa. So the frequency is precisely kappa at the origin. And in fact, for dimension 2, an analysis of homogeneous harmonic functions in the half plane shows that these are the only possible value of the frequency in the thin obstacle problem. This analysis was done by Richardson in his thesis. So you can do, it's an easy calculation, it's an easy exercise to show that if you look at the Signorini problem in dimension 2, then there are only two possible values of the frequency. They are either of the type 2m minus 1/2 or the type 2m. So they are either even integers or even integers minus 1/2. So there is an open problem in dimension n bigger than or equal than 3, but I don't know the answer to this problem, and I don't think it's known. Okay? So is whether it is possible to have free boundary points which in the thin obstacle problem where you can have other values of the frequency.
And what is your guess?
I don't have a guess because I have had long fights with Luis Sylvester and with Arshak, and then in the end we always convince each other that each one of us is wrong. So my guess is that it's not possible, like in the two-dimensional case. But any guess is good here. In three dimension, the situation is substantially different. So regularity of the free boundary at regular points. So as I told you, the frequency always has the value bigger, at least 3/2. So you start thinking, what is the situation at points where the frequency is exactly 3/2? These points are called regular points. They are the analog of the points that Henrik discussed yesterday for the solution, for the half-plane solutions, okay? So in this situation here, in the thin obstacle problem, the half-plane solutions are those solutions of the Signorini problem whose frequency at that point is equal to 3/2. So those are called regular free boundary points. And the analysis of regular free boundary points was exhausted by Atanassopoulos, Caffarelli, and Salsa, and subsequently in another fundamental paper by Caffarelli, Salsa, and Sylvester. So Atanassopoulos, Caffarelli, and Salsa, I should say that this result here is relevant to zero obstacle, flat manifold, 2007. Subsequently, in 2009, Atanassopoulos, Caffarelli, and Salsa were able to deal with the case of non-zero obstacle, but the analysis there becomes much more complicated. I will not discuss this at all because it becomes very much involved technically. So what they proved is that if you have a solution to the Signorini problem, then the part of the free boundary which is composed of regular points, so this is that part, is locally a C1 alpha regular n minus 2-dimensional surface. By the way, you might wonder, you have seen Henrik has discussed this question. What happens, there is this fundamental result, 1977, Kinderlehrer and Nirenberg, if in the obstacle problem you know a priori that your free boundary is of class C1, then it is in fact real analytic. In the thin obstacle problem, this is a completely open issue. How to go to higher regularity of the free boundary once you know that is C1 alpha. Nobody knows how to deal with this. A former student of Harshak, Wen Hui, she's in fact in Germany working with Herbert Koch on this. She has some partial results, okay? But very partial results. I mean, the situation is completely open at this moment. So, singular free boundary points. So I told you about the regular free boundary points. So there is a group of two groups of people who have completely settled the question of the initial regularity of the free boundary at regular free boundary point. What happens at singular free boundary points? Now, singular free boundary points arise also in the classical obstacle problem. For instance, if you take in three variables x squared plus y squared times a constant, which makes the Laplacian equal to 1, then you have a coincidence set which is confined to the line to the z-axis, and so all the points are singular free boundary points. So in the classical obstacle problem, I'll tell you later, the analysis of singular free boundary point was done by Monod relatively recently, okay? And in the thin obstacle problem, you may say that the point of the free boundary is singular if it has vanishing n-1 density at the point. Okay, so I will show you examples of singular free boundary points in a moment. So the singular portion of the free boundary, this is a theorem, by the way, is precisely composed by points at which the frequency is an even integer. You can prove, using the monotonicity of the frequency, and this was done in my work with Arshak, that if you have a singular point, then the frequency has to be an even integer, okay? So, I mean, here there is, you know, in terms of the rescaled functions, these are the rescaled functions. Saying that 0 is a singular free boundary point is equivalent to saying that the coincident set of the rescaled function intersected with the thin manifold as vanishing n-1 Hausdorff measure. So let me denote with the sigma kappa the collection of all singular free boundary points whose monotonicity is equal to kappa. Remember that kappa, we already know, has to be an even integer. It can be 2m minus 1/2, or it cannot be anything else. It has to be. Now, it is important to observe that singular free boundary points cannot be neglected, because the free boundaries can be made of all singular free boundary points, like in this example. You take this function here. This is a solution to the Signorini problem with 0 obstacle, okay? And you see the free boundary of this solution to the Signorini problem is made up completely of a singular free boundary point. The origin is a singular free boundary point of monotony of frequency 4. Points on the x1 axis are, you know, of frequency 2, and so are points on the x2 axis. So all these points are singular. All these points, notice the sigma that appears everywhere. So this function here, for this function here, the free boundary is made up all of singular points. So you have to worry about the singular set of the free boundary. Okay, so similar to the classical obstacle problem, there is a central objective that in the study of the regularity of the free boundary, and it's the uniqueness of the blow-ups at you know, at the free boundary points. In this case, would be singular free boundary points. Now, proving this uniqueness is equivalent to showing that at that singular free boundary point, one has a Taylor expansion like this. So where P is a non-degenerate homogeneous polynomial of a certain order kappa, which we know has to be 2m, okay? And P is a harmonic polynomial, which is homogeneous of degree kappa, and it's non-negative on the thin set. And it's even in the variable xn. All right, So this, obtaining this Taylor expansion here is the heart of the matter. You know, proving this Taylor expansion is the whole thing. If you get this Taylor expansion, then you can show the uniqueness of the blow-ups. And then you can go on with the analysis of the regularity of the free boundary. Now, I already said this thing, so let me talk a little bit about historical development at this point. So in the classical obstacle problem, the uniqueness of the blow-ups of the rescaling, so these were the rescaling that were used by Luis Caffarelli, you know, the uniqueness follows from the following deep result, which has already been recalled several times in these lectures, and it's the Alt-Caffarelli-Friedman monotonicity formula. The Alt-Caffarelli-Friedman monotonicity formula tells you that if you take a minimizer in the classical obstacle problem, which is 0 at 0, then this quantity here is monotone increasing, okay? And as you have seen from Henrik's lecture, this result is mostly used to prove the regularity of, you get regularity result for higher order derivatives, and that when you look at the rescaled functions, okay? So, oops, where am I? Okay. So, subsequently, later, Georg Weiss, oops, sorry, there is no E here, it's Georg. Georg Weiss discovered a simpler but beautiful monotonicity formula and showed that with such formula one can still prove uniqueness of the blow-ups if you are at regular free boundary points, okay? So Georg showed in 1999 in his Invenciones paper that if you have a solution to the classical obstacle problem, then this quantity is, which is related to the epiperimetric inequality of Reifenberg, is monotone increasing. And one has, in fact, the derivative of this, I'll call it the Weiss functional, or the Weiss functional is expressed by this formula. And you see that the derivative vanishes precisely on functions which are homogeneous of degree 2. Now, unlike Almgren's monotonicity formula, which allows for any monotonicity, in Weiss formula, W prime is 0 if and only if there is a fixed degree of homogeneity, which is typical of the classical obstacle problem. So, more recently, Regis Monod has used Weiss result to prove yet another monotonicity formula, another beautiful monotonicity formula, which is tailor-made for the study of blow-ups as singular free boundary points in the classical obstacle problem yet still. Okay, so a free boundary point in the classical obstacle problem is called singular it is, if it has vanishing n-dimensional density. And here is Monod's monotonicity formula. So take a minimizer in the classical obstacle problem and suppose that 0 is a singular free boundary point, then for any arbitrary harmonic polynomial which is bigger than or equal than 0 and homogeneous of degree 2, this function is monotone increasing. And this monotonicity formula is tailor-made to give you uniqueness of the blow-ups at singular free boundary points. Okay? So, unfortunately, whereas in the classical obstacle problem the frequency has only one possible value, kappa equal to 2, in the thin obstacle problem we have seen that there are infinitely many possible values of the frequency. So when you blow up, you can get all possibilities, I mean at least the possibilities 2m and 2m minus 1 as results of the blow up. The 2m are the singular free boundary point. So all right, so I've already talked about this. So with this observation in mind, and with the objective of studying singular free boundary points, I mean, Arshak and I tried constructing an analog of Monod's formula based on Almgren's frequency formula rather than on Weiss. So this was suggested by the fact that, at least in principle, Almgren's formula does not display any limitation in the specific value of kappa. And this is already brought up by Eugen in his lecture. I believe it was his first or second lecture when he talked about the generalization of a Weiss formula to every possible values of the of homogeneity. And I will recall this formula now. Okay, so in the process of looking for this monotype formula, we discovered a one-parameter family of Weiss-type monotonicity formula, which are in fact equivalent to Almgren's frequency formula. And so let me, so this is the formula that was mentioned by Eugen in the harmonic case. So now U is a solution of the thin obstacle problem, any kappa bigger than or equal than 0. Let's consider this functional here, which is a generalization of Weiss functional. Then it turns out that the derivative of this functional is given by this formula here. So you see that this functional vanishes if and only if U is homogeneous of degree kappa. Okay? So if kappa is equal to 2, then in this result here we obtain back a Georg Weiss result, except that here he has a characteristic function of the set where U is bigger than 0, but that's it can be made completely analogous to this fact here. Okay, so as I have already mentioned these things here. So let me denote by p kappa the family of harmonic homogeneous polynomial of degree kappa, which are positive on the thin manifold. So this is the class p kappa. And then here is the monotype monotonicity formula that Arshak and I proved. So suppose that you have a solution to the thin obstacle problem, and 0 is a singular point of the free boundary, and we know that the frequency has to be 2m. Then for an arbitrary polynomial in this class p kappa, this functional here is monotone increasing. And this was our key result to break into the uniqueness of the blowups. Okay. So anyhow, so notice that when m is equal to 1, and kappa, so m is this guy here. So when you have kappa is equal to 2, then the above monotonicity formula is precisely mono, except that this is relevant to the thin obstacle problem. So you have to take into account more, I mean, a situation is trickier, okay? So as I've said, you know, with this result in hands, we were able to prove the desired Taylor expansion for the blowups, and therefore we got the uniqueness of the blowups, and then it was kind of smooth sailing. I mean, the technology is at that point standard to prove the regularity of the free boundary. Okay? So, how much time do I have? When do I stop talking?
Anytime you like, in the next.
That is a dangerous statement.
In the next 10 minutes.
Okay, in the next 10 minutes. Oh, but my watch is completely screwed up. Is that 10 o'clock? Yeah. I had 20 to 10. So then when you said anytime you like, I said, ooh, I can talk forever. Oh, okay. No, don't worry. So 10 minutes, right?
Yes.
Okay. So let me exit this, and where is it? Okay. So I want to discuss now a little bit, very briefly, the parabolic Signorini problem. Okay, and as I said, this is joint work with Donatella, Arshak, and Tumton. So let me start with a little picture here. So semi-permeable membranes and osmosis. All right, so we have a membrane which is permeable only to a certain type of molecules, which are solvents, and blocks other molecules, which are the solutes. So because of chemical imbalance, the solvent flows only in one direction, okay? So the solvent flows through the membrane from the region of smaller concentration of the solute to the region of higher concentration, and that's called osmotic pressure. The flow occurs in one direction, and it continues until a sufficient pressure builds up on the other side of the membrane. Okay? When this happens, the flow shuts off. The process is called osmosis. All of us have tried these things in kindergarten. At some point, we tried this little experiment with absorbent paper. Oh my goodness, I am a dinosaur. There is no absorbent paper nowadays. I'm sure the kids don't even know what it is.
In historical laboratories.
Huh?
In historical laboratories.
I see. Okay. So mathematical formulation, unilateral problem. So we have an open set in Rn. M, which is the manifold, the thin manifold, is a semi-permeable part of the boundary. So we have a function phi defined on M cross 0t because time is involved here now. And that's the osmotic pressure, which represents the thin obstacle. And we have U function from omega cross 0t to R, the pressure of the chemical solution. And the pressure satisfies diffusion equation. You look at the book by Duvaux and Lyons, you'll find this thing here. So on MT, there is the following boundary condition, which are called finite permeability. So on the region where U is bigger than phi, remember phi is the osmotic pressure, then there is no flow. Here is the condition of no flow. On the region where U is less than or equal than phi, then you get that the normal derivative of U is a multiple of U minus phi, and there is flow. Okay, so here is the picture. No flow in this region, flow in this region. So letting lambda go to infinity, remember lambda is this parameter here. We obtain the following condition on MT, which are called the infinite permeability, and these are the Signorini condition. Okay, these are known as the Signorini boundary conditions. This problem is known as the parabolic Signorini problem or parabolic thin obstacle problem. So the function U solves the following variational inequality here. And U belongs to this class kappa, which is the same as in the elliptic case. Okay, so solution exists and is unique. This is standard fact by now. All right, so that's the motivation of the parabolic Signorini problem. So we have the free boundary and the coincident set as before. And the only difference is that now these are sets in space and time. So you can think of this as a portion of a boundary of a cylinder. So let me go to what was known. C1 alpha regularity. Nina Uraltseva in 1985 established that if you have a sufficiently smooth obstacle and initial datum phi 0 on lip, and G in L2, then the solution is C alpha alpha over 2. Remember that this is the parabolic anisotropic class. So here C alpha means regularity with respect to the space variable x, alpha over 2 regularity with respect to time variable. So the gradient is alpha Helder continuous in space and 1 alpha over 2 Helder continuous in time. And this is an interior local result. So this is a very important fact. This is the counterpart of what I mentioned before. It was 1979 result by Luis. Okay? So, all right. And there were no known results for the free boundary. So in the case when M is flat, we have proved the following result. So this is one of the main results in my joint work with Donatella, Arshak, and Tung To. So suppose that U is a solution to parabolic Signorini problem with flat M and obstacle phi sufficiently smooth, then the gradient of U is C1 half 1/4, and this result is sharp. So there is the gradient. Remember that in the elliptic case, There is no 1/4, of course. Here you have that the gradient of u is c1/2. Here you can show that the gradient of u is Elder continuous with exponent 1/2 in space and 1/4 in time. And this result is optimal. You can check it on the time-independent solutions, of course. Let me talk about Poon's monotonicity formula. So Poon was a student of Fang Guan Lin, and he worked on a generalization of Almgren's monotonicity formula. He wrote a cute paper in the late 90s on this generalization of Almgren's monotonicity formula to the heat equation. And what he showed is this. So suppose that u is a caloric function in this strip here, then this quantity here is monotone increasing. This g is the Gauss-Weierstrass kernel for the backward heat equation. It has to be the backward heat equation, can be the forward heat equation. Otherwise, monotonicity is destroyed. There is a very important reason for which you have to take the backward heat equation. So, in a way, there were ancestors of this formula, which is Michael Struve's monotonicity formula for harmonic maps. Okay, but this formula is it goes a bit deeper than Struve's monotonicity formula. And then you can see from from the proof that this function here is constantly equal to kappa if and only if u is parabolically homogeneous of degree kappa. Parabolically homogeneous means this. So homogeneous with respect to the standard parabolic dilations. So as I said, G is the Gauss kernel, and notice that the variable is here. Okay, so that is the backward Gauss kernel. All right, so I will again make a normalization. I will consider a solution to the parabolic Signorini problem with zero obstacle. And now, oh my goodness, he got up. Am I done?
No, you still have this
You are
courtesy meeting.
You're intimidating me.
Okay, go on.
Courtesy minutes is, am I finished? I mean, if I'm finished, I will stop here.
Yeah, okay, 1 minute.
Okay, 1 minute. All right, so let me just tell you the story. Here, for the heat equation, things go completely different from than Laplace's equation. The reason, even when you are in zero obstacle, the situation becomes much more complicated. And why? Because if you look back at Poon's monotonicity formula, this is a global result. Here, it tells you you're taking a solution in the in a whole strip. When you work with the heat equation and you want to analyze the parabolic Signorini problem, you have to localize the problem. I mean, it's a local problem. So in some way, you have to cut off. When you cut off, then you lose the property that if you take a solution of the heat equation multiplied by a cutoff function, it's no longer a solution of the heat equation. I'm saying a triviality, of course. But that triviality imposes lots of complications in the problem. Because now you have to work with this function here. So you subtract the obstacle, that's fine. Think of the obstacle being zero. The complication is still there. But you have to multiply by a cutoff in order to localize. When you multiply by a cutoff, you get that V solves this monstrous equation, and you have to take care of all these dirty terms that show up. And then...
They are localized where you get the cutoff.
They are localized where you get the cutoff, but still, that destroys monotonicity. That's the problem. Okay. So you have to deal with these things. So anyhow, we were able to prove a variant of the monotonicity formula of Poon that that is this result here. But look at this result. It's a spurious monotonicity formula, apparently, because it contains this term here, and now you're taking the logarithm of the maximum between the height function and an appropriate power. The appropriate power is designed in order to take care of the growth of the cutoff at infinity. So anyhow, so this quantity is monotone increasing, and that was the main tool that allowed us to crank the machine and stuff. Then we had to prove Weiss type monotonicity formula, Monod type monotonicity formula, and so on and so forth. And in the end, we were also able to prove, besides the optimal regularity, the initial regularity of the free boundary. But it's a huge paper. If you want to suffer, it's in archive.
How many pages?
90 pages.
Oh my God.
Don't read it.
This should be forbidden.
Yeah.
Okay,
Right. Thank you.
The schedule, but in any case, since this is the last day, let's give like 3 minutes so that Eugen will begin at past 15, right? Okay? 3 minutes of relaxation.
3 minutes.